Hey kids, it's Matt here. Got solution for you on Unit 5, AP Classroom, Unit 5 FRQ. Now, this one's a good question. It brings in a lot of energy, coordinates, mechanisms, gas laws. Boy, there's just a whole lot going on in this problem, and I don't think it's particularly hard, but let's walk through the solution together, make sure that we're all on the same understanding. So this first one starts out and it says it's got the high equation. And I say the high equation, remember, because this is H plus I gives us HI, the high equation. And when you see that equation, that should kind of be a nudge for you. Hey, you're probably going to be doing something with rates, because that is the quintessential rates equation or rates question equation. So, excuse me, we've got a reaction coordinate and it says H2 and I2 react to produce. And in this case, we have an exothermic reaction. Basically says carefully complete the energy level diagram by drawing a curve that accurately shows the progress beginning at the reactions, moving through a transition state, and ending at products. When adding the products to the diagram, be sure to use an energy level appropriate. So they're trying to be nice and say, hey, by the way, remember it's exothermic, so draw us there. So we're going to start here. We're going to go up to a transition state and make sure that we're exothermic and come down and say that our HI is over here. And it says moving through. It didn't say label it, but you know what? I'm just going to give them a little bit because I'm positive I know that that's happening there. And the appropriate energy level. On the energy level diagram, draw a dash. So now that's it, right? Super easy. And B even gets better. B, it says, hey, draw a dashed line on the curve. Okay, no problem. Because those are always going to be the catalyzed pathway. Doot, 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 doot. Show the progress as a suitable. I don't want that there. You get out of there. I want that over here. There's a catalyst. Okay. And then C is a great question. C says, on the diagram, draw a vertical line segment with a length that corresponds to the activation energy of the reverse reaction, the EA of the reverse. Still not trying to be difficult here, kids, but here is C. Let's go up to there. Let's go down to there. That's the reverse E sub A. That's what that activation energy looks like. Once again, I don't think it's hard chemistry, and I think the questions are pretty clear as well. So that gives us a good energy level diagram, and that's half of this. Then there was a second question, and the second question involved for parts of the free response, involved magnesium being placed into some hydrochloric acid and making magnesium chloride and H2. In an experiment, we put a small piece into a beaker, we had some HCl, and a reaction occurred. We've done this reaction, right? Okay, write a balanced net ionic for this. This is something I'm starting to see more often, is the AP is wanting balanced net ionics. That's new to the game. They haven't done that much in the past, but we can do that. So if we've got the overall, what I'm looking at is I see Cl aqueous and Cl aqueous. Everybody else is going to participate here. So my balance net is going to be Mg solid plus 2H plus aqueous goes to Mg aqueous plus H2 now as a gas. It didn't say states of matter. I'm going to put them just because in a net ionic, we really should put those if we can. And this is following the same rules we followed all year. They gave us states of matter, so let's be polite and let's give them states of matter back. Do make sure it's balanced and we're okay here. All right. Now, B is a really fun gas law question. It says, student collects some H2 and he measures it. And this was done by collecting a gas over water. We've done this. After carefully analyzing it, all right, the volume is to be measured at 45.6. Okay, great. The atmospheric pressure in the lab is 765 and the equilibrium pressure of water is 24 K. It wants to know in number B1, what is the pressure inside the tube due to H2? Well, this is a Dalton's law, gas law, collected over water, gas collected over water. So here we go. We're going to have the pressure, P tote equals P gas plus P H2O, excuse me, because that gas is wet. So the pressure of the gas is going to be the atmospheric pressure, 765 torr minus 24 torr. So the gas pressure is 741 torr. Now, 2 says, okay, what are the number of moles of HCl in this? As soon as you see moles, you should be thinking, hey, they gave us a whole lot of data up here. They gave us, let's gather it, 298K. They gave us 45.6, and we just calculated 741. So this looks like it's shaping up to be an ideal gas law. And here's what I've got. First thing I got to do is get this torr to atmospheres. And the reason I got to do that is so that I can use R. I don't have an R value in torrs. So this is 0.975 ATMs. Then go PVNRT, 0.975 ATMs. The volume they told you was 0.456, 45.6 mils, or liters in this case. Okay, that's going to equal N. R is 0.082 liter atmospheres per mole Kelvin. And they told us we were at 298 Kelvin. So if I munch and crunch them, N ends up being 0.018 moles. So they went from stoichiometry and stoichiometry to partial pressure into an ideal gas law. Now let's see what C holds to us. C is going to bring in some bonding. And C says, in a different experiment, they're going to make the classic substitution. They're going to make a BA instead of an MG. Well, remember, MG is way at the top. BA is way down at the bottom of column 2. So what do we have? Explain the difference. There's greater reactivity. And that's due to the ionization. Why is the ionization greater? This is the same answer we had in Unit 1 or Unit 2 about atomic structure. Mg has less nuclear charge. It's a fancy way of saying protons, less nuclear charge. Therefore, electrons are held less tightly. Okay. But because BA has more shells, more shielding, lower ionization energy, and more reactive. Now you're asking yourself, why did I have to put in that first part about magnesium? Because we have to do it in terms of atomic structure. Magnesium has less nuclear charge. Barium has more of a nuclear charge, but it has more shells, more shielding, and a lower ionization energy. I feel the need that they're going to want two rationale for these. You've seen that in a lot of these AP reviews. They want a lot of 2-point validations. Okay, I've got two more real quick ones on this. Then they shift gears now and go to a mechanism. And they tell us the slow step is up first. And they say, write a rate law for the overall reaction. The rate law just comes from the slow step. Rate equals K, concentration of H2, concentration of ICl. Boom, done. Take it from the slow step. There's no substitution. They're giving you a slow first step. You just take it from that first step. Remember, the rate law doesn't come from the overall reaction. The rate law comes from the mechanism of the slow step, or of the slow step of the mechanism is a better way of saying that. Okay. Then on E, they come back and they circle around full circle. Back to our energy diagram now, our coordinate. And they say, hey, now draw out, okay, draw a curve that shows the following: the activation energy of 2 steps and the enthalpy change for the overall reaction. Okay, so they told us it's exothermic. So I've got a 2-step, first step is slow, second step, and the whole thing is exothermic. The enthalpy change for the overall, boom, there's delta H. Step 1 is higher than step 2. Doesn't have to be pretty. Mine certainly isn't, but that gives us a great walkthrough of a question, or 2 questions actually, that relate rates, mechanisms, gas laws, rate laws, all tying it together. Great question. I'm Smath. I hope this video helped you.